6.6 is the last section in Chapter 6. In Chapter 6, if I were to name it anything, I would call Chapter 6 similarity, because anything that's proportional is or are similar to each other. That's the same thing with these dilations. When you have an object that gets dilated or made bigger by a certain scale factor, it is similar to the previous shape, meaning all its angles are still congruent, but their sides are proportional. You are used to seeing dilations every single day when you reduce things or enlarge them, when you pinch or when you unpinch, I think is the word. I think that's what it's called. I mean, literally, that's what the algorithm is. The person who programmed your cell phones, who created the software, when you pinch and unpinch, it literally zooms in and dilates every single letter to stay in the same proportion. That's how it works. The easiest questions you will have today will deal with reductions and enlargements. The reduction means it got smaller, enlargement means it got bigger. And you can pretty much tell if something got bigger or smaller. That's not a hard question at all. Easy questions. Make sure you know that when the scale factor is greater than 1, it's going to create an enlargement. And when it is less than 1, it is going to be a reduction. If you say something's a reduction, then your scale factor should be less than 1. That's what N stands for. Our textbook, and I believe the worksheet that I passed out to you, uses a capital D, and the capital D stands for a dilation. And then they usually will give you a number inside parentheses, and that number represents what your scale factor is. So when I see big D with the 1.5, that's telling you that your scale factor is 1.5 times bigger than what the original shape was. The center is sometimes given. Not always, just sometimes. If there's a number, that is your scale factor. The second thing is your center. You don't always go off of the same center. Sometimes your center is outside of the shape, like this example, where there is a projection of one shape into its image. We call this a projection. But sometimes, if things are lined up on top of each other, they might share a side, and one of the corners might be the center. Or sometimes if it's on graph paper, you guys might see the center at 0, 0. It just depends on the problem. Do not always assume the center is going to be at 0, 0 or outside the shape. It could be on the shape or it could be inside as well. Now, the nice thing about dilations is that all the proportions, all these ratios are equal to each other. And it's the neatest thing, in my opinion, mathematically about a dilation. When I look at a dilation, look at how many different fractions are equal to each other. What that tells me is, it doesn't matter if I'm talking about this image, top right, over this pre-image. The after divided by the before. This divided by this is going to equal this divided by this, which is going to be equal to this divided by this. All three of those ratios are the same thing as the scale factor reduced to lowest terms. As a matter of fact, you could even measure the distance from the center to the image, any single point you wanted, and divide that from the center to the original. That would equal the same thing. I could draw a line from C to Q prime and measure that and divide it by C to Q, and I would get the same ratio as the scale factor. Every single one would match up, including the X direction and the Y direction would be in the same measurements. So that's something that we're going to use to our advantage as we get into our problems. The first few examples that I have for you are going to be somewhat easy, I think. This is number 5 on your worksheet. Feel free to grab your worksheet and do this with me if you'd like. Hardest part, in my opinion, it says you have to figure out which one is the original and which one is the image. Image means after. pre-image is before. The solid is a dilation of the dashed line figure. The solid is a dilation. That was what happened after. The solid is the after. The solid is the image. So this is the after and the before is the dotted. Tell whether the dilation is an enlargement or a reduction. Enlargement or reduction, say what you think it is out loud. Go for it. Enlargement. I agree. Then find the scale factor of the dilation. Now here's the nice part about the scale factor. It doesn't matter which side you pick. You can pick, okay, this is the dilation. It is 1, 2, 3, 4 units on the top here, and I can check the original is 2. And you could take that and you could reduce it to lowest terms. And you can figure out what the scale factor is. The scale factor is 2, aka 2 to 1. I would accept it in either way. 2 is probably the easiest way to write it, so that's probably the way I would prefer it. This is an enlargement, and the scale factor is 2, or 2 to 1, twice as big. And the neat thing about that is it doesn't matter if I pick this side. 1, 2, 3, 4, 4 over 2 is still 2. Or if I pick the bottom, 1, 2, 3, 4, 5, 6, 7, 8. 8 divided by 1, 2, 3, 4. 8 divided by 4 is 2. Every single side gets multiplied by the same scale factor. It's kind of, even the diagonals. This is 1 root 2. This is 2 root 2. Look at that. It got multiplied by 2. It's very cool that way. Now let's get to something that's a little bit harder, a word problem. When you look at the problems for 9 through 11, remember you're looking through a magnifying glass. So I'm going to do my best job at drawing what I like to say is a magnifying glass. And in this magnifying glass, you're going to see a ribbon. And maybe the ribbon down here is something that just kind of goes like this. And maybe it's a two-stranded shape in one of these. Maybe you saw something like this recently in a bio class. I'm not sure. And then over here, you see this thing. It's a little bit more zoomed in on it. And you see, oh, look at that. It's a double helix or something along those lines. You look at an object, the image of a ribbon is 10 times. This magnifying glass does something. It enlarges whatever you see by 10 times the amount. 10 times the ribbon's actual size, and the image of the ribbon has a width of 1 centimeter. So from here to here on the image is 1 centimeter. We need to find the actual dimension of the object. So how wide is it here? That's the question. If this is now 10 times bigger, then what that means is that this 1 centimeter got multiplied by 10. So if I want to know what the original width is, all you have to do is do the opposite, which is divide by 10. And you could either leave this as a decimal with centimeters, or you can go and use your knowledge of the metric system, and you could say 0.1 centimeters, a tenth of a centimeter, is the same thing as 1 millimeter. Either one is correct, by the way. Yes, sir?
So you don't want it in fraction form, you want it as a decimal?
Well, it didn't say. I would accept any of the forms. Fractions are what I prefer, though. I just thought maybe I can get out of a fraction and go right to a whole number by doing millimeters. So remember, with the magnifying glasses problems, you're looking through it, and what you see, the measurement is over here on this side, and you have to find the original. And then what happens is we're going into number 14. Number 14 says a dilation has center of 0, 0. Find the image of each point for the given scale factor. So there might be a bunch of different points on the coordinate plane. I'm going to insert here an XY axis just so I can have something. And then what I'm going to do is I'm going to go 1, 2, negative 3 to the left, 1, 2, 3, 4, 5 up, and I'm going to put the point P is right here. And then what I'm going to do is I'm going to have the center is at 0, 0. Forgot to label this as 5 because it is. And that's where point P is, and we need to do this capital D with a 1.2 of point P. That's what the parentheses P means. We're going to need to dilate point P by 1.2 times, meaning it's got to be 1.2 times bigger. And whenever you have a scale factor that is 1.2 times bigger, that also works in the X and Y directions. So if I went 3 units to the left and I want to go 1.2 times bigger, then it's very simple to do 3 times 1.2 times bigger, and you could figure out where your new point would be. My new horizontal component, my new X, would be negative 3.6, because 3.6 is 1.2 times the amount of negative 3. And the number 5, since 5 is the vertical component, we went up 5 units, and I wanted to go 1.2 times bigger than that. I'm going to multiply by 1.2 times the 5. For my, this was horizontal component, this is now my vertical component. That makes 10, 5 and 1, that makes 6, 6.0 in the vertical direction. Find the image of each point. So that means P prime is going to be at a new location. P prime is going to be at the location of negative 3.6, 6. What that tells you is that if I went horizontally negative 3, 3.6, if this is negative 4 and this is 6, negative 3.6 up a bit, P prime will be right there. P would be there, P prime would be there. It's getting 120% bigger is my guess, is what it would be. That's only 1 point, but the 1 point is there. If the center was not at 0, 0. If the center was over, let's say, over here, you would see how far is it going to the in the horizontal direction. You would multiply by whatever your dilation is. If you're only going horizontally 2 units to the right, you would multiply that by 1.2 times. If you're going vertically to that spot, 2 units, you multiply that by 1.2. And then you would know where from the center where you would need to go. Your new point would be at that other place. The center at 0, 0, don't assume it's always going to be 0, 0. It may move around. As a matter of fact, that's one of the reasons why I have 23 here as well. The very last few problems that you have, 21 through 23, are going to ask you to do a dilation, but they don't have any coordinates, so it's not like this is on graph paper for you. What you have to do, you have to dilate something by 0.8. Hopefully you know that that is a reduction. And you're doing the dilation about the center point, C. C is your center this time. I'm going to put the center right here. And we need to dilate triangle BCD. How do we do 0.8 on triangle BCD? How do we take every single point and reduce it by 0.8? Here's how we're going to do it. You're going to measure BC using a ruler. And if you have a ruler and you measure this as 5.3 centimeters, and by the way, That's 5.3 centimeters because I've expanded mine. It's not going to be 5.3 centimeters on yours, but it doesn't really matter, to be honest with you. Okay. For example, if I went like this, like now look at me, and when I measure it, it's totally bigger, right, than the 5.3. Matter of fact, let me just make this easy on myself. Let's pick a nice whole number. Let's try to see if I can get it to be 5 on the dot. There we go. 5.0 centimeters. Yay! You're going to measure your own, whatever it comes out to be, and I'm going to say use the metric system because it's going to be easier for your decimals. 5.0. I need to go 0.8. I need to know how far from here I need to go. I'm going to multiply this by 0.8, 0, 40, move the decimal 2 places. I need to go, instead of 5 centimeters, what do I need to go?
4.
So now I have the 5 centimeters. My new point from point C needs to be 4 centimeters. This is where B prime needs to be. I'm going to do the same thing over here for D. From C to D is 11 point. I'm going to be more accurate, as I think it's 11.6. I'm going to go right to the edge of the black line. And I'm going to take that 11.6 and I'm going to multiply it by 0.8. Take my calculator just because for speed. 9.28, which is almost 9.3. I don't think I'm going to get any closer than 9.12. 9.28 is right about there. And this is D prime. Now, if I think about it, and I were to try to measure C, how far away is C from C? Because I need to measure from C to C. It's 0 units away. Multiply it by 0.8. Guess what? C is going to stay exactly where it is. So now, I have now moved all 3 of these points. Here is BD prime. Here is B. This is BC. This is also C prime, isn't it? And lastly, D prime to C prime. And we have this new image. This new image is on top of the other one. It is 0.8. It is 80% of the original size, with the center being at point C, which is the same as C prime. Do you notice that they're all still parallel? Makes sense to me. We're going to stop your notes right there.